Hey everyone, in this quick video I'm going to talk about Kirchhoff's voltage law, or KVL, but in AC circuits. You might already know what KVL from DC, but when we bring in AC circuits things get a little bit more interesting, but don't worry, I will keep it simple. So, KVL basically says that if you go all the way around a closed loop in a circuit, the total voltage adds up to zero, or in other words, the voltage from the source equals the sum of all the voltage drops in the components. In DC circuits, voltages just add up nice and straight, but in AC, since they're not in phase, we can't just say V source equals VR plus VL plus VC directly, which is the KVL formula you would use for DC circuits. Instead, we have to think in terms of phases, kind of like arrows pointing in different directions. And this is where the formula changes a bit. What are phases? A phase is a rotating vector or complex number representing a time invariant sinusoidal waveform with a fixed frequency and a constant amplitude and phase. As you can see here, we have a simple RLC circuit with an AC voltage source. KVL does still apply, but you just have to add as phases, aka vectors. So here, I'm demonstrating how Kirchhoff's voltage law, or KVL, works in an AC circuit, specifically a series RLC circuit. We've got a resistor, an inductor, and a capacitor all connected in series to an AC supply. The values are up on screen in the top left corner. In AC circuits, voltages and currents are constantly changing direction, so we can't just add voltages directly like in DC. Instead, we use phases, which let us handle both the magnitude and phase angle of each voltage. For this, first I calculate the reactances. That's the opposition of the inductor and capacitor to AC. For the inductor, the formula is XL equals 2 pi FL. And then for the capacitor, XC equals 1 over 2 pi FC. Then I also worked out the current, which came to be about 5.29 amps. And then using that current, I found the voltage drop across each component, which is just for VR it's I times R, for VL it's I times XL, and for VC it's I times XC. Now you might notice that the voltage across the inductor and capacitor are actually much higher than the supply voltage, because if we were working with the DC circuit and we had these values, you would see just adding all of those values would be like 300 almost, probably more. But because they're out of phase, we had one leads the current and the other lags it, so they partially cancel out. To check KVL in AC form, there's a vector equation, which is VI equals square root of VR plus VL minus VC squared. When you plug in all of the values, you will get about 100.6 volts, maybe lower, maybe high, depending on how you rounded, which matches the supply voltage of 100. That shows that KVL still holds true in AC circuits. We just have to add voltages vectorically instead of in a straight line. So what did we learn today? Kirchhoff's voltage law means the total voltage around any loop adds up to zero. It still works in AC, we just use phases, and when we use phases, a different form of KVL applies, and phases are in place due to the current and voltage are always changing directions.